All right, so I want to start by apologizing. This is going to be completely heteronormative and mono, not polyamory. All right. So the requirement here is that you have boys and girls, and each boy and girl will state whether they liked each other or not, and we want to make the Pope happy, and by making the Pope happy, we pair them up so that each boy marries one girl and each girl marries one boy. It's hopefully the same one that married her. Right? Everybody get what our problem is? So this is called maximum matching in a bipartite graph. Right? This is a bipartite graph because we have two sets and the edges only go between them. All right, one of my things my father's famous for is solving this problem in general graphs, but here that's way harder than we're going to do. All right, everybody get the problem? So here you'll see we've matched 3 people, and but John isn't married, and neither is Beth. Right? So one thing we could see is, can we get John married? Well, how do we get John married? He would have to marry Mary, but Mary is married to Fred, so Mary would divorce Fred. And then Fred could marry Anne, and Anne could divorce Bob, and Bob could marry Sue, and Sue could divorce Sam, and Sam could marry Beth. Right? It would be what I call a great day for lawyers. Right? And then we have a matching. Everybody buy that? So here's an algorithm for it. It's often fun to say, given an algorithm for one problem, how do you give an algorithm for another problem using that as a subroutine, right? So it's a reduction. So here, suppose we knew how to solve network flows, right? What we're going to do is we're going to build this graph where these are the boys and these are the girls, and we put an edge here if this boy is willing to marry this girl, right? Oh, and then we get an extra node S, which is a source for the boys and a sink for the girls, right? And then we're going to add some requirements. The first requirement is that the edge coming to each boy is going to have a capacity of 1, right? So he's going to get a flow of 1 in. So how much can flow out? Only 1, right? So that's how we can restrict that this boy can only marry one girl. Right? Does that make sense? And so similarly, we're going to put a capacity here of 1. So the girl is draining 1, so she has 1 flow out, so she can have at most 1 flow in. Right? Does that make sense? And you can have the capacities in the middle can be infinite, doesn't matter. And this will give us a good flow, a good solution. Does that make sense?
What if the flow is 2 instead of 1?
Here, 2? Well, that would be saying the girl can drain 2, so she could marry 2 boys.
Okay.
Right? Does that make sense? Now, and then we do max flow here, and we look at where the flow is. If there's flow flowing along, right? If there's a flow of 1 from here to here, then we say there's married. And if there's not flow, right here, this is a flow of 1, so either there's a flow here of 1 or there's a flow here of 1, saying this boy can marry this girl or this girl. Right? Yeah?
I don't get what we're trying to get at. Like, there should be equal flow on both sides.
All right, so what is our network flow? Says that if this has capacity 1, then the most flow you can have here is 1. Right? And so the flow out has to be 1. Right? So these edges have capacity infinity, but it doesn't matter. You only have 1 flow out. So you can either put a flow here or a flow here of 1, meaning that the boy can only marry 1 girl. Right? So we're trying to get the max flow here. And so we would have to argue that if we have a max flow, we can translate that into a marriage. And if there is a marriage, we could translate that into a max flow. So we get that these 2 problems have the same set of solutions. Right? Does everybody understand that? Yeah?
If we don't have like
Well, by definition, the maximum matching is, you might not be able to get a total matching,
Yeah.
but the best matching you can get is called the max matching.
Okay.
So that would equal the max flow.
Yeah.
Right? Everybody get this problem? Now, let me add a little subtlety here that the Pope didn't think of. Right? Who said our solution needs to be integer? Right? I have a flow in here of 1. I need a total flow out of 1. What keeps me from marrying half of her and half of her? I'm just saying. You have to keep your boxes open. Right? So, but in fact, the algorithm that we're going to present here, if the capacities are all integers, then everything that happens will be an integer, and we will never get a non-integer, so we'll get an integer solution. All right? But that's often not the case. So in many, many problems, you can take this problem, which is NP-complete, and industry would love to solve, and what it wants is integer solutions. If you relax it so that your solutions don't need to be integers, then you can solve it using linear programming. But then you're going to have these non-integer solutions, and you have to do some probabilistic rounding to try to get an integer solution. All right. Yes?
Wouldn't the half and half split prevent other people from getting their full married stuff?
Well, one, they could marry half of this person and half of this person too.
The one where they only have half, but then this one has, they only have one person that they like, but
Right.
then this person's taking half of that.
Yeah. So I'm not trying to come up with an example in which a non-integer solution is a better solution. I'm just saying it is a possible solution. And when you open up the range of possible solutions, the maximum could be better by including one of those. Right?